Hi, our team chose the swim fin project. We are Karina, Melanie, Raina, Kalel, and Michael. We all understand the importance of exercise and staying active throughout our life. For individuals with prosthetic devices, swimming is a great way to do so, as it inflicts less wear and tear on the soft tissue as well as the prosthetic itself. Our client, a 52-year-old veteran with unilateral transtibial limb loss, desires to swim more but faces the issue of his prosthetic limb feeling like an anchor and weighing him down in the water. He also cannot conveniently switch between his land-compatible prosthetic foot to his water-compatible swim foot, therefore tasking the team with an action of designing a novel solution that will allow our veteran to do so. We have designed a unique attachment mechanism for a pre-existing swim fin to our veteran's foot, with the goals of minimizing drag force, increasing convenience, and boosting his ease of use.
For our project, we'll be using the Omega amphibian flip fin. The way that the fin is flipped down is by kicking the fin in the water, which activates it into the down lock position. The weight varies from 3 to 6 pounds to 4.4 pounds based on the size of our prosthetic foot. The current way to flip the fin back into an upright position isn't viable for the veteran, so two ways to change the mechanism is through a rod and wire method. For this method, we will be using 3 gears and 1 brass rod. The gears will weigh approximately 0.2 pounds and have a diameter of 66 millimeters. The rod will weigh approximately 3 pounds and have a length of 387 millimeters, in which we found was the average length of the knee to ankle of an average human male. The corrosion rate of brass was found to be 30 years, so corrosion won't be much of an issue in this method. We will also include a bumper system so that the fin doesn't over-rotate once flipping up. The rod will be detachable so that it is easy to transfer, and it will also have a strap made of TPE to secure the fin and 2 hinge attachments also to secure the fin. For testing, we will test the gear efficiency, which we will do by comparing the output and input torque required to rotate the driving gear against the resistive torque being applied to the final driven gear. We will also test the corrosion rates of the brass to make sure that it will last a supposed 30 years.
And here we have a basic CAD assembly of our main rod model. We would like to have the rod run down the lateral side of the client's prosthesis, starting at the side of the knee and running down to the ankle. The bottom of the rod would attach to the first gear, which would attach to the second, allowing for the system's directional pivot to properly align with the client's foot. And then the third gear would attach to the second at a 90-degree angle. This third gear would also attach to the fin, and I will explain why in the next slide. For the design of this method, once again, it will include the Omega swim fin, 3 brass gears, a brass rod, and 2 bumpers and 2 hinges. And its operation will entail inserting the removable rod into the first gear of the system and rotating it in order to activate the second and third gear, which is attached to the fin and hinges in order to bring the fin upwards to a 90-degree angle and back downwards, while keeping it out of our client's way when walking. The bumpers included into the design are intended to prevent the client from over twisting the rod and extending the fin too far.
We plan on doing some tests on this mechanism, and what we would like to see from these tests are that the brass lasts 30 plus years without corrosion. We would also like to see that the input torque applied to the brass rod is the same as the output torque that the gears apply to the swim fin. We would also like to see a reported ease of use from the veteran, and we would also like to see that the fin does not move without the use of the rod, meaning that the fin is stable and locks into place.
For the wire method, it will differ from the rod in that we will add a shell to the outside of the socket to hold the wire. A hole will also be added at the bottom so that no water stays inside the mechanism, which could possibly increase corrosion rates. A locking mechanism would be added so that once the fin reaches 90 degrees, it will lock in place. The wire would have a similar spring mechanism to a tape measure and be made of stainless steel for corrosion resistance, high tensile strength, and durability. The testing that we will be doing is testing different wire materials in terms of ease of use. We will also be testing the length of the wire so that the fin will fully lock. And finally, we'll be doing a corrosion test of both the wire, whichever material we choose, and stainless steel.
For the wired method, we made a single CAD model. This is the side view of the CAD model, and the fin itself is color-coded in blue. The bumper used to prevent the fin from overextending is colored in green. The pylon is colored in white, and the wire is colored in red. If we look at this, we can see the path that the wire would travel. It starts at the top of the fin and goes all the way along the fin up and then travels up the pylon where the wire could be pulled. If we look closely, we can also see the two locking mechanisms on either side of the fin. These locking mechanisms, the position of these locking mechanisms becomes more apparent if we look at the top view, where we can see that there's one on the right and one on the left. We can also see a top view of how the wire travels and a top view of the bumper. Here is a front view of the fin that shows the height of the fin along with the height of the bumper and the height of the locking mechanisms. So for the results of the wire method, we decided to test 3 different materials for the wire: stainless steel, nylon, and polyester. Out of these 3 materials, stainless steel was found to be the most optimal. It was highly resistant to corrosion. It had the highest minimum breaking strength out of the 3 materials tested. However, the stainless steel wire weighs considerably more compared to the other materials. But this should not be a major factor. This is because in our testing, we found that we needed a minimum of 400 millimeters of stainless steel wire to control the fin effectively. This would mean that if we use the stainless steel wire, it would only weigh an extra 64 grams.
Our team set out to design a mechanism different from the ones available on the market, specifically ensuring that there is no push power required to flip the fin up. In the primary design, the client uses their upper body, specifically their arms, to twist the rod and activate the gears in order to move the fin upwards. Even in the secondary design, using the wire running up the leg, the client will use their upper body to pull the wire up and move the fin up. The result yielded that most of the primary design is made up of brass, so it doesn't corrode easily, it's fairly lightweight and durable, and TPE adds rigidity where it needs to be. In terms of testing for the primary design, the 4 tests devised were corrosion resistance of material used, measurement of the input and output torques of the gears, reported ease of use by the veteran, and testing if the fin stays locked in place when it's used. The testing environment would be in the water when looking at the corrosion resistance and ease of use, as well as if this fin stays locked in place. The wire can be created out of stainless steel and wire rope when comparing the corrosion resistance with the maximum loading parameters and breaking strength. For the wire design, our team can perform a series of tests to figure out which material would be best for the wire and compare the minimum breaking strength, safe load, and corrosion resistance. There are still some design weaknesses that the team could improve on. One of the drawbacks of the primary design is the weight. 7.5 pounds isn't extremely heavy, but it's also not very lightweight. In order to make the design lighter and not get in the way of the client's daily activities, the rod could be detachable. One of the largest potential weaknesses in the secondary design is that the wire could get tangled up and wrapped around the leg, which could be dangerous or inconvenient for the client. One way to combat this issue is similar to a manual locking knee, where there is a shell outside of the current socket which would hold the locking mechanism. This could all be incorporated on the side of the socket away from the major components of the socket, pylon, and prosthetic foot. To conclude, although 2 different designs were pitched in this report, there are so many aspects of each design that can be improved upon and changed based on the client's individual needs and expectations.
This is by no means a universal device, but with more research and testing done on mechanisms like the ones presented in this report, the future can hold more advanced and easy-to-use prosthetic device attachments that can cater to every client's needs.